Hello, and welcome to York Observatory's monthly TeleTube broadcast, the online astronomy and astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the AICO Observatory, located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every last Friday of the month at 7:30 p.m. local Toronto time. For any questions or comments you have about our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Instagram at the handle YorkU Observatory. We would like to inform you about the opening and call for applications for the Summer 2025 Astronomer in Residence program. This program is a collaboration of the Alani Carswell Observatory with Kalani Provincial Park to host astronomers in the certified dark sky site of Kalani, to lead in-person presentations and shows using the park's observatory. To learn more about the program, its requirements, and the application process, visit our website at yorku.ca/science/observatory/AIR. Good evening, everyone. I'm Denelle, and I will be one of your hosts this evening, along with Alex, Darius, Dev, Hector, and Maheen. Tonight, we've got a wonderful guest speaker, John Wilmot, joining us, who we will be introducing shortly. The observatory at York campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many Indigenous nations. The area known as Takaronto has been taken care of by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many Indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. Now, Alex will tell us what is up in the sky.
Thanks, Denelle. So, good evening, everyone. At 7:30 p.m. tonight, the sky offers us several celestial sights for you to enjoy. If you look up, Mars is prominently visible after sunset, so it's only going to set around 4:15 a.m. Look towards the southern sky to spot its distinct reddish hue. Mars will be positioned near the constellation Orion, making it easier to locate. For the best view, find a location with minimal light pollution and a clear southern horizon. Jupiter can also be seen after sunset, but it sets a little bit earlier around 1:30 a.m. It outshines most stars and will be located near the Pleiades in the Hyades cluster, in the constellation of Taurus. To find Jupiter, look towards the western sky shortly after sunset. A pair of binoculars can enhance your view, and potentially reveal some of its moons. Interestingly, Sirius is also up in the sky, and I have a super cool story about that. Sirius is the brightest star in the night sky, and it disappears throughout the year for a period of time of about 70 days. In ancient Egypt, Sirius was closely associated with the god Osiris, the deity of afterlife and rebirth. Interestingly, the ancient Egyptians believed that this 70-day disappearance marked Osiris's journey throughout the underworld, and it influenced their tradition of taking exactly 70 days to complete the mummification process. So when Sirius finally reappeared in the dawn sky, this is known as the heliacal rising. It symbolizes rebirth, not just for Osiris, but for the soul of the deceased. It's a beautiful example, of how ancient cultures use the stars to guide both their rituals and beliefs. Finally, there's a partial solar eclipse coming up tomorrow morning. And if you are up at sunrise about 6:30 a.m., the moon will partially be covering the sun, creating a crescent-shaped sun. So ensure you have the proper eye protection, such as eclipse glasses, to safely enjoy this event. Now that we've explored what's up in the sky tonight, I'll pass it over to Mahim to introduce our guest speaker.
Thanks, Alex. Hi everyone. Our guest speaker for tonight is John Wilmot. John's interest in astronomy began in childhood with constellation identification in Cub Scouts at Scouts Canada. After a period of casual observation with small telescopes, his passion deepened in 2004 with the purchase of a Sirius telescope and subsequent involvement in a local astronomy club. Following a brief hiatus, he resumed the hobby, quickly completing the Royal Astronomical Society of Canada's Explore the Universe program. Currently, he is engaged in sketching the Messier objects and serves as the director of the Barrie Astronomy Club, where he presents on astronomical topics. John has also delivered presentations at the Barrie Public Library, sharing his enthusiasm for the night sky with both adults and children. We are very happy to have John join us tonight, and I will hand it over to him now to start us off with the presentation.
Thank you very much. Thank you for having me. Uh, Let me get up on the screen. I hope you can see this. I'd like to talk to you tonight about measuring the night sky. I've got three different ways that we use to measure the night sky. They go from very basic to more complex, but hopefully this will work out. So what we're going to cover tonight, we'll quickly go through calculating your latitude because that's always fun. Next, we'll measure the sky using your hand. We'll measure the sky using the altitude and azimuth system. And we'll measure the sky using the right ascension and the declination system. Basically, I'm going to explain how these systems work. I won't really measure anything in the sky. But let's start with finding your latitude. If you can imagine that this circle is the Earth, we have an axis of rotation, goes through the North Pole and South Pole. At right angles to our axis of rotation, we've drawn an imaginary line around the middle that we call the equator. I think everyone's familiar with that. York University, we're here about halfway between the equator and the North Pole. If we draw a line from the center of the Earth out to York University, we get an angle. That angle is our degrees of latitude. Now, how do we find that, or how do we calculate that? Or an easy way to measure it? Well, if I draw the line at the horizon, it's actually a tangent to this circle. It's right angles to that radius, that red radius. It's the horizon that we see is a tangent. I often think that flat earthers don't understand how tangents work, and that's part of their confusion. But we also are fortunate that our axis of rotation points to a star, Polaris, that we call the North Star. It's not exactly at Polaris, but it's close enough for our estimation. And if we're standing at York University, oh, sorry, if we're standing at York University looking at the North Star, those two lines, for all practical purposes, are going to be parallel, right? The radius of the Earth is only a little more than 6,000 kilometers, but the distance to Polaris is 446 and a bit light years. So those two lines are practically parallel. If I drop that line down to the equator on the diagram and I extend that horizon line, I've now created two right angle triangles. And of course, right angle triangles are great. I've got a red triangle here, and I've got a blue triangle over here. And if I draw a line across the top there, I'll get a third triangle. And what's so special with triangles is if we're looking for this angle X, we know that because any triangle is 180 degrees when you add up all the angles, we know that Y is 90 degrees minus X. But we've also got a right angle over on the other side, on that bottom of the blue triangle. So X plus Y is 90 on the other side as well. And if that angle is 90 minus X, then up there at the top of the blue is also X. We flip across to the orange, that's Y, and we come down to the bottom of the orange triangle, that's X. And if you look, that orange angle X is the line between the horizon and the North Star. So that's an easy way that we can find our latitude on the Earth. Triangles are great, right? Well, we gotta love triangles. You know what they say, if you love triangles, every triangle is a love triangle. Measuring angles in the sky. So how are we going to do it? A simple way. You hold out your hand. Hold your hand out at the full extent of your arm and put up your little pinky finger. The distance or the amount of sky that you cover with your little finger is about 1 degree. It's not going to be perfect, but it's close enough for rough measurements. If you put up your 3 middle fingers, that's 5 degrees. If you clench your fist and put it up, that's 10 degrees. If you spread your index finger and little finger, that's 15 degrees. And if you spread your thumb and little finger, that's about 25 degrees. Now, none of this is 100% accurate, but it's a good rough system. And I know what you're asking. Wait a minute. I've got small hands. My fingers are skinnier than yours. Or I've got big hands. The thing is, someone with small hands will usually have small arms as well. Somebody with big hands will have big arms. So on average, for most people, this will work. It's not perfect, but it is pretty good. And you can find your way around the sky using these hand measurements most of the time. And let's see how we can do that. Up in the sky, we have 7 bright stars that a lot of people will recognize as the Big Dipper. It's not a constellation, it's an asterism. It's part of Ursa Major. It's not the whole of Ursa Major, but it's bright stars, easy to find and easy to use to check to see, is my hand really going to be 25 degrees? Well, end to end on the Big Dipper, from the tip of the handle to the tip of the bowl, is 25 degrees. And if you stick your hand up, you'll find that your hand is very close to that, if not exactly on. Right? But the Big Dipper is a great measuring tool because from the second star of the handle to the tip of the bowl is 15 degrees. So that's the spread of your index finger and little finger. And then the two stars at the end of the bowl of the handle, they're about 5 degrees. So the next time you're out looking at the Big Dipper, just put your hand up there, see if you can get the same measurements, and you'll find that it's probably going to be very close. Not perfect, but it's very close. So what do we use this for? Well, we already talked about finding our latitude. This is a view from the astronomy program Stellarium. It's a free program that you can download. This is a view from York University, 9 o'clock tonight, looking north. And if we look up in the sky, we can find the Big Dipper. Over on the other side is Cassiopeia, the constellation Cassiopeia, sometimes called the Lazy W. Now, we already said 25 degrees tip to tip on the Big Dipper. If we take the 2 stars at the end of the bowl of the Big Dipper, we call these the pointer stars, and draw a line between the stars and continue it down, if we measure down about 25 degrees, it's slightly more than 25 degrees, but if you put your hand up like this, you'll come to a reasonably bright star. That star is Polaris, the North Star. So we've already used our hand to measure the sky to find the North Star. But we talked about our latitude. What's the distance or the height of the North Star, or the angle between the horizon and the North Star? Well, we can use our hands again. We measure 25 degrees, another 25 degrees. We've gone too far. Let's back that up. Let's put in 15 degrees. 25 degrees, 15 degrees, that's 40 degrees, a little bit more, and we would get our latitude. I'm going to say if you guess that that's 3 to 4 more degrees, you'd be pretty close to the latitude of York University. So that's how we can start to use these to find our latitude. But there's uh, lots of other measurements in the sky that we can use. We've got Cassiopeia, the lazy W. You see one half of it does look kind of lazy. The other half is pretty sharp. It forms more of a triangle. If we imagine that as a triangle and then shoot a line from the base of the triangle through the tip and then measure along from the base, along that line, you come to another reasonably bright star over here. It's called Mirach, and it's in the constellation of Andromeda. If we come back about 5 degrees and down slightly, you're going to find a fuzzy patch in the sky. Now, this is you will not see it from York University because of light pollution. If you're in a dark sky, you might be able to see it. But if you are out in a reasonable sky, maybe you'll see it, maybe you won't. But if you've got this method of measuring and a pair of binoculars, you'll definitely see it in your binoculars. But this will tell you where to look with those binoculars. All right, let's look at another one. Going back to the Big Dipper, we already used the pointer stars, but we can use these other 2 stars in the bowl of the Big Dipper and shoot a line across the sky and then measure 10 degrees from the bottom of the bowl out to a patch of sky over here. Now, this object you will not see with your naked eye, but you will see it in a telescope and you'll probably see it in binoculars. This is M81. It's called Bode's Nebula, but it's actually a galaxy. But when Bode's looked at it, he didn't know what he was seeing, so he called it a nebula. But that's a way to find that galaxy. And M82 is very close as well. So once you've got one in your field, you can search around and find the other. If we turn to the south, we can see the winter hexagon is still in the sky. Sirius, Procyon, Pollux, Capella, Aldebaran, and Rigel makes a big hexagon of bright stars that are up all through the winter. If we go up to the top to the star Capella and shoot a line down, not through Pollux, but through his brother Castor, we get this direction. If we measure 10 degrees from Castor, we come to M44, which is known as the Beehive Cluster. It's an open cluster. It's just a grouping of stars that look very nice in a telescope and also in binoculars. There are all kinds of different measurements that you can do with your hands to find these different objects. You can look it up in star charts, what's so many degrees from this or so many degrees from that. Sometimes you'll see news articles published where it says this thing is going to be 5 degrees southeast of the moon. You can use your hand to make those measurements to find these objects. This system works very well with binoculars. So from this first part, what are our takeaways? Well, first of all, we can find our latitude by measuring the angle of the North Star above the horizon. You can use your outstretched hand to measure these angles in the sky. Remember, it's 1 degree, 5 degrees, 10 degrees, 15 degrees, 25 degrees. Find objects in the sky by estimating their distances from known stars. And this works very well when you're using binoculars. If you've got a telescope with a mount and it's, got registration marks and more accurate pointing system, you don't need this. But if you're just out with binoculars or just out naked eye, this works well. And of course, who doesn't love triangles? All right, altitude and azimuth system. This is a slightly more advanced system. It's a more accurate way to measure the sky. It does usually rely on some tools, but it's a simple system, simply based on measuring up and down and left and right. That's all you're really doing, right? It's measuring the sky based on you and the horizon, and wherever you are, you're at the center of this system. The problem with it is the measurements you take don't translate to any other position and really don't translate well to other times. And that should become clear when I explain how this system works. Imagine you're in the middle of an open field. You can see the horizon or close enough. We've got cardinal directions of north, south, east, and west. And 5,000 years ago, the Sumerians came up with a system of dividing a circle into 360 degrees. They sure loved the number 60 back then. They passed a lot on to us. Not the greatest system in the world, but that's what we have. All right, so if we see a star up in the sky, we look up there and say, I wonder, or I want to know where that is. I want to measure where that star is. Well, first thing we do is from north, from 0 degrees, we can drop a line from the apparent position of the star down to the horizon and then measure the angle from 0 degrees at north around past 45 degrees around to the position where the star appears to be above the horizon. Let's say in this case, we're talking at 62 degrees, just for the sake of argument. So we have an azimuth of 62 degrees. We would measure that with a compass, or if we had a telescope set up oriented to the north, you can measure it using the telescope measuring tools. Next problem is to measure how high in the sky that star is. That's angle X. How do we find angle X? Well, it's simply a matter of measuring from the horizon up to the star, as we did with the North Star. But what happens if you're not at a perfectly flat horizon? You know, if you're out in a boat on the ocean, sure, you can see the horizon. But if you're at York University, there are buildings in the way. If you're in a lot of different places, there'll be buildings, there'll be houses, there'll be trees, mountains, all kinds of things where it's hard to find the horizon. The way you would find it is by using a level, or if you don't have a level, if you were to imagine a line that came from the center of the earth straight up through your feet, it would point straight above your head to a point in the sky that we call the zenith. The easy way to find that is, which way is gravity going? Look in the opposite direction, you're looking at the zenith. If you measure down from the zenith, that's y. Y is 90 minus x. So we can measure either up from the horizon or down from the zenith. We can figure out x is 35 degrees. So we have an altitude of 35 degrees. Now this altitude and azimuth works great for us standing here in this field. It would be fine if, you know, you're next to me and I want to give you a direction to look. I could give you that altitude and azimuth and you could find it. But if somebody's in another country, in a distant place, that star will not appear at the same altitude and azimuth as it does for us, because this is centered on us with this system. The other problem with this system is when you look at the sky, the stars appear to move. Most of that movement is actually the Earth rotating, but from our point of view, if you just stand and look at the sky, it looks like the stars are moving across the sky. So if it's at altitude 35, azimuth 62 right now, wait 15 minutes, it will be in a different location. So there are limitations to this system, but you can measure different stars with it. You can get these measurements, and you can compare different stars if you're quick. Here we are lying on our back looking straight up at York University, right? And the alt-az system is centered on us and the zenith directly above us. These are the lines of azimuth and altitude. The circles are the altitude. The straight lines in this picture are the azimuth. Now, it's a little easier if we stand up and look to the north. So this is what we're doing here. You can see that we're looking due north here. We can see the Big Dipper. We can see Cassiopeia. We can shoot that line. We can find Polaris, the North Star. Now notice here, Polaris is not exactly on the north line. Polaris is very close to our north celestial pole, but it's not exactly. It's off looks like it's off by about 1 degree. Now, we can't say that its azimuth is -1 degrees. We can't measure azimuth in negative numbers. We have to measure in positive numbers, which means we have to go around to the east, which is counterclockwise as we look to the north. And here we go, measuring all the way around. Instead of being 360 degrees around, let's say we've gone 359 degrees. But we get an azimuth of 359 degrees. Now, altitude is a lot easier to measure. We just go from the horizon up 20, 30, 40 degrees plus a bit. How much how much between 40 and 50 degrees? Not quite half. How about 44 degrees? Well, of course, we already knew that the altitude of Polaris was going to be 44 degrees, a little bit less, because we're at York University and we know our latitude. So that's how the alt-az system works, right? It is an accurate way to measure the sky. You are using some tools. You find a compass bearing to get you the azimuth, and then you find the angle above the horizon, and that gives you the altitude. Wherever you are, you're at the center of this system, and because of that, the measurements you take don't translate to people in other locations, but you are measuring the sky. Let's go on to a more complicated system, right ascension and declination. On the Earth, we have a system of latitude and longitude, and we can designate any point on the globe. You pull out your phone, it will know through GPS what your latitude and longitude is. You can look that up very easily these days. But the Earth is rotating and orbiting. So we move, and our latitude and longitude moves relative to the sky, right? Everything in space is moving, right? But some things are so far away that even though they're moving, they do not appear to move, not to us, right? If you imagine you're standing at York University and someone's walking along the sidewalk in Los Angeles, they are moving, but you would never be able to see that they are moving, right? It's the same kind of distances that we're talking about here. The distance to the stars is so far that even though we know they're moving, to the naked eye, you can't see that they're moving. But we can't project our latitude and longitude, but we can project our axis of rotation, our north and south pole. We can project those into the sky. Likewise, we can project our equator into the sky. And that's what we do with the right ascension declination system. If we imagine, as the ancients did, that the sky is the inside of a great sphere that surrounds the Earth, we can look at it and draw latitude and longitude, a latitude-longitude grid onto the sphere. Not the same one that we have on Earth, but it looks the same as the one on Earth. But it's stuck to the sky instead of stuck to the ground. The poles of the Earth and the equator of the Earth are the same as the poles and equator of this celestial sphere. So we are locked together. The sphere remains fixed while the Earth rotates within it. It looks to us, as you stand outside under the stars, it looks like the sky is moving over top of you. And for a long time, people thought that's what was happening. But in fact, it's the Earth is rotating, the Earth is orbiting, we're moving. The sky is practically standing still. Not really, but it practically is. Let's look at this. So imagine this is the Earth with lines of longitude and latitude. You've probably seen these kinds of lines. Right? We've got our North Pole, our South Pole. That's the axis that we rotate on. We've got the equator, which is just a perpendicular line to the axis of rotation. From there, we can project our equator out into space to create a celestial equator. Right? It's not on any firm object, but it is the same line all the time in space. Because we are rotating, that's always the dividing line between north and south for us. Once we have a celestial equator, we create a celestial sphere. Now, obviously, this is way closer to the Earth than stars are in real life. The stars are not painted on a sphere, but sadly, it appears they are. So, with the celestial equator and celestial sphere, we can then designate a north celestial pole, a south celestial pole, and we can start to measure or put lines on the sky. If we say the equator is at 0 degrees, we can measure away from the equator. Away from the equator is what declination means. It means to move away from. And we can measure the declination from the equator. To the north, we can draw lines all the way up to the North Pole. From the equator, it's 0 degrees. To the North Pole is 90 degrees. So north declination is 0 degrees to plus 90 degrees. We have to say plus 90 degrees because if we go to the south, that's negative 90 degrees. So when we talk declination, it can be any number from minus 90 to plus 90, with 0 being exactly on the celestial equator. All right. So that's what we mean by declination. We're just measuring how far from the equator something is. Now, right ascension is like the lines of longitude on the Earth. The thing about the lines of longitude on the Earth and lines of right ascension in the sky is they all converge at the North Pole and at the South Pole. So the distance between them varies depending on what declination you're measuring at. But if we think about longitude and latitude on the Earth, in 1884, a bunch of scientists, 25 countries sent representatives to Washington, D.C. They decided that the line of 0 longitude is going to go through the Royal Observatory in Greenwich, England. So they fixed where the prime meridian would be. In space, there is no Greenwich, England that we can look at. So where do we set a 0 line in space? Well, fortunately, there's another line in space. Our planet orbits around the sun and our axis is tilted 23.4 and a bit degrees off of the orbit of, or the axis, or the plane of the orbit. Gives us our summer and winters. But what's important is it also creates a line in the sky called the ecliptic, which is the path of the sun. Now, everyone is familiar with the sun going across the sky in the day. Looks like it comes up in the east, goes down in the west. That's a function of our rotation. It's not going across the sky. We're turning as we look at it. We also orbit the sun. As we orbit the sun, the stars that appear behind the sun, like Sirius for the Egyptians, the stars that appear behind the sun seem to change month to month. Because just like if you're in your car driving past the shopping center, right, and you see a telephone pole, it looks like the telephone pole is moving across the front of the shopping center because of the perspective. You're the one moving, the pole is staying still, but it looks like it travels across the shopping center. And it's just a function of perspective. The same thing's happening with the sun. As we orbit the sun, it looks like the sun moves. The sun, although like everything else in space, although the sun is moving, for this situation, we're orbiting the sun. We're going to pretend that the sun is staying still and we're just going around it. Now, this ecliptic can be seen in the sky. It goes through 13 different constellations, 12 of which are the zodiac of astrology fame, right? If you've got a birth sign, it's because the sun was supposedly in that constellation on the day you were born. That's how the astrologers work things. I said it goes through 13 constellations, but we only count 12 in the zodiac. That goes back to the ancient Sumerians who loved the number 60, and 13 is not a factor of 60. So poor old Ophiuchus doesn't get to be part of the zodiac. Anyway, we have these two lines that cross at two different places. They cross at the fall equinox and they cross at the spring equinox. And it's at the spring equinox, the vernal equinox, that we have decided that we are going to put our celestial meridian. On Earth, we have the prime meridian, goes through Greenwich, England. In the sky, we have the celestial meridian, goes through the point that the sun is at on noon on the day of the vernal equinox. So now we have a 0 point for our right ascension. Here we are looking at the sky again. We're looking north. The last grid I showed you was centered or appeared to be centered on the zenith above your head. This one, right? We're in the northern hemisphere. We've got the Big Dipper, Cassiopeia. We've got the North Star. This grid is going to look like it's centered on the North Celestial Pole, right? Again, Polaris is not exactly at the North Celestial Pole, but it looks like it is. Now, how does this work? The circular lines that we see here, those are our declination. The straight lines are our right ascension. Our prime meridian is over here. And we mark that, we measure, not prime meridian, sorry, our celestial meridian is over here. We measure right ascension in hours, right? So from the celestial meridian, we go around 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, 6, 7, 8, 9, 10, all the way around 20, 21, 22, 23, 24 hours in a day. The reason we call these hours is because it takes an hour for the sky to appear to move the distance of these lines. Now, think about it. When the sky appears to rotate, these lines all appear to rotate as well. So if you're looking due north here, and you see that that was 20 hours, if you waited an hour, 21 hours would then line up with due north. All right. Declination, same thing. Declination, we measure up from the celestial equator, 20, 30, 40, 50, 60, 70, 80 degrees, 90 degrees plus because it's the northern hemisphere. So this is the system that we're using. Now, how do we talk about it? Right ascension notation. We measure right ascension in hours, from 0 to 23 hours, because just like on a clock, you go from 23:59 to, we say 24 hours, but when we write it, it's always 0 hours and so many minutes, so many seconds. So there's 24 hours in a day. It takes a day for, or it takes 24 hours for the stars to appear to go around in the sky. So we talk about how many hours, and our notation, as you see, is a small h. Then we divide the hours, just like in real life, into minutes because they do match. Right? The hours get divided into 60 minutes, 0 to 59, and the minutes get divided into seconds, 0 to 59, 60 seconds in a minute, 60 minutes in an hour. The notations are small h, small m, small s. So if we look at a right ascension notation, it would look like 5 hours, 16 minutes, 41 seconds. So we can measure where that is, and we can add to it, subtract from it, and that's our notation for right ascension. Our declination, as we talked about before, it's in degrees, degrees away from the equator. It can be to the south and be up to minus 90, or it can be to the north, positive 90. And that's in degrees. Now, thanks to our ancient Sumerian friends who divided everything by 60, we divide our degrees into minutes as well. These minutes are not the same as minutes of time. They're not the same as minutes of right ascension. But when you divided a degree up, you divide it into minutes because that's what we've done for 5,000 years. When you divide a second or a minute up into 60 seconds, we have the same system. Now, to distinguish these minutes that are related to degrees from the minutes related to right ascension, we'll sometimes call these arc minutes. Right? And you'll see that notation. Something is so many arc minutes wide or arc seconds wide. And you can when they say arc minutes, they're talking about these kinds of minutes. They're not talking about the right ascension minutes and seconds. Now, these minutes and seconds, or arc minutes and arc seconds, never change. They're always the same amount of distance on the sky. But just as we know that lines of longitude converge at the North Pole, and as you come south, they get wider apart until they hit the equator they're at their widest point, then they start to converge again at the South Pole. Same, the lines of right ascension do the same thing. They start all at one point on the North Celestial Pole. They widen as they get towards the celestial equator, and then they narrow. So a minute changes depending on how far north or how far south you're looking. The distance on the sky changes. At the equator, a right ascension minute can be 15 times as long as an arc minute. But at the North Pole, it can be even less, right? Because those lines go out and they come in, there's no fixed distance on right ascension minutes. They vary depending on where you're looking. But the amount of time it takes for them to pass is always a minute. So when we talk about declination notation, we would say something like plus 45 degrees, 59 minutes, 43 seconds. If we're already talking about declination, we know that these minutes and seconds are unique. Okay, let's look at the sky. We're looking south again. Here's the winter hexagon again. There's the bright star Capella. Let's measure that. All right, before we can measure, I have to show you over here on the right is the celestial meridian. We measure from the celestial meridian in hours. How many hours have passed? Right? 1, 2, 3, 4, 5 hours. If Capella is a little more than 5 hours behind that celestial meridian, it's between 5 and 6 hours. It's, what are you going to say? It's a quarter of an hour. So a quarter of an hour is 15 minutes. Right? So we've got right ascension 5 hours, 15 minutes. Let's measure declination. Here's the celestial equator. We measure up from the equator in degrees, 10, 20, 30, 40, 50. All right. So it's between 40 and 50. It's a little more than halfway. We'll say 46 degrees declination. So right ascension, 5 hours, 15 minutes. Declination, 46 degrees. Using this same system, we could measure any star in the sky. And because these lines always move with stars, these lines rotate the same as the sky rotates. It's fixed on the sky. Capella's right ascension declination is always going to be that. So if I'm looking at it here at York University and someone is in Vancouver looking at it, I can say 5 hours, 15 minutes, declination 46 degrees, and they'll find the same point in the sky. So this is why right ascension declination is the universal system that we use for measuring the sky. Now, when we look at Capella, its actual right ascension and declination, when we read it out, accurately measured, it's right ascension, 5 hours, 16 minutes, 41 seconds. So I was wrong there by a bit. We get a vertical bar to separate the two. Then then declination plus 45 degrees, 59 minutes, 43 seconds. So I was a little short on that one. This is how we express right ascension declination notation. And you can, just like with longitude and latitude on the Earth, you can designate any point in the sky using this system, and everyone will see the same thing. So, to recap, we project our axis of rotation and our equator into the sky. We imagine the sky as the inside of a sphere, and we put a longitude and latitude system onto that sphere. It's a standard method that we use for referring to any celestial object. And never forget that right ascension minutes and seconds are different from declination minutes and seconds. We use the same name, it means different things. Sometimes you'll see arc minutes, arc seconds to make sure you're thinking of divisions of a degree and not divisions of time. So that's it. What have we gone through? We talked about finding your latitude and how it's equal to the angle of the North Star above the horizon. We looked at how you can use your outstretched hand to measure the sky. We decided that altitude is the height of a celestial object appears above the horizon. Azimuth is the compass bearing to the point on the horizon below a celestial object. Right ascension is the distance from the celestial meridian. Declination is the distance from the celestial equator. And that is my presentation. Do you have any questions?
Thank you so much, John. That was a really enlightening presentation, and we do indeed have some questions for you.
Okay, go ahead.
Starting with Darius. Oh, sorry, starting with Alex.
Hey John, thanks for that presentation. That was awesome. So I was wondering, since the sky is a sphere itself, how do hand measurements account for curvature when measuring larger, angular distance between objects?
Okay, interesting question. With these hand measurements, they are really just a rough approximation, and they're only useful for short distances. We wouldn't measure 180 degrees using hand measurements. That would kind of be ridiculous and almost impossible to do. So I don't think the curvature really has much effect on the way we measure. All we're looking is a short distance uh, um, angular difference between two objects. So I wouldn't use the hand measure for uh, larger angular distances.
Cool, thanks.
Next, we have Darius with a question.
Hi, John. Also,
Okay.
thank you for the great presentation. That was really cool. My question is, how do you recommend getting started for new people who are interested in amateur astronomy?
Okay, that's a great question. Uh, Amateur astronomers love to get this question because we all have our own opinions. Um, I'm going to say that the first two things you should get if you're interested in amateur astronomy, first two things you should get is a good book and a pair of binoculars. Now, I know everyone wants to rush out and buy a telescope. They go through Costco and they see, oh, here's a telescope, it's 150 bucks. I'm not sure about astronomy. I don't want to sink too much money into it. Do not buy that $150 telescope. Spend that money on binoculars, you'll get a much better set of binoculars. Those crappy little telescopes that advertise you can see 600 times magnification. If they're advertising the amount of magnification, they're what we call a hobby killer because someone will get out there, they'll point at the sky, they won't see what they're hoping to see. A decent telescope starts at $500. You can get good telescopes used for $500. My brother got into astronomy. He bought a 8-inch Dobsonian telescope, and I think that's probably one of the best starter telescopes there are. If you want to jump right in both feet, go to the used telescope market and find uh, something like an 8-inch Dobsonian telescope. But when I was researching for the telescope I wanted to buy, I was getting there's all kinds of information you can get on different types of telescope and what they're supposed to be good for and what they're not good for, and what do you want to do. I found that it's a lot like shopping for a car. If you went to a car dealership and said, I want a car that'll go 0 to 60 in 3.5 seconds. It has to be good in the snow, and I want to take it camping because I got a lot of stuff to put in the back. And you know what? Sometimes I drive my kids and their friends to school, and I want to have lots of seating. That car doesn't exist because it's impossible for that car to exist. Same thing. If you say, I want to look at objects in the solar system. I want to look at things deep sky. I want to take photographs. I want to be able to see craters on the moon. I want to see this. I want to see that. There is no one telescope that does everything. Telescopes are specialized, and some of them are very specialized, just like some cars are very specialized. But an 8-inch telescope is not huge, but it's a good amount of light. With telescopes, it's not how much magnification, it's how much light you can get. 8 inches is a good number. I mean, 6-inch telescope, you'll get good views. 8-inch, you'll get better. So 8 inches is about the sweet spot for a starter. Dobsonian telescope is cheap, easy to get into, and if you don't like it, you're not killing yourself. I'd already had my 8-inch Dobsonian years ago. When I bought a new telescope, I bought a Schmidt Cassegrain 8-inch, and part of my consideration was how much it weighs. You know, I'm not weak, but you know, I'm retired. I'm getting older. I want to be able to carry this around. I want to take it from the car to the dark site, set it up, all this kind of things. If I bought a 50, 60 pound, oh, sorry, if I bought a 40 kilogram, a 30, 40 kilogram telescope, I wouldn't be able to move it, or it would be so awkward to move that I wouldn't use it as much. So you want to consider, are you going to be able to move it around? And people with these giant size telescopes, they also start to build their backyard observatory. And that's a whole long way into the hobby. But if you're just starting out, I say get a good book, get a good pair of binoculars, and then find an astronomy club. Go there, talk to people there. I've never met someone who wouldn't let you look through their telescope if you were, respectful and going to treat it well. Um, People in astronomy are very friendly. They want to help each other out. And if you say, I'm new, I just want to see what it's like looking through a telescope, 9 times out of 10, they're going to say, yeah, come on, take a look at mine. Now take a look at his, and now take a look at hers. So starting out, get a book, get binoculars, and find other people that are in the hobby. Kind of a long answer, sorry.
No, John, I thought that was very comprehensive. Thank you. And I've got another one. What object in the night sky do you usually look for first when you go out observing? And what about it interests you?
Okay, so what object in the sky, in the night sky? Well, the night sky is different throughout the year. Things we see in the summer, we can't see in the winter. Things we see in the spring, we can't see in the fall. So each season sort of has its targets. Um, I'm right now working on the Messier object list. A guy, Charles Messier, was looking for comets, and he looked up in the sky and he knew that a comet was going to look like a little smudge. Well, he found all kinds of smudges. He found 110 smudges in the sky, none of which were comets. So he made a list so that when he was looking for his comets and he, you know, found that smudge and he checked the right ascension and declination, it's already on his list. That's not a comet. He doesn't have to waste his time with it. He was not looking for these objects, but he made a list of objects of what not to look at. But they're beautiful objects. They're nebula. They're globular clusters. They're open clusters. They're galaxies. There's all kinds of beautiful things up there. What I like to look at, um, last summer I was at an astronomy meeting called Starfest. It's a very big one put on by the North York Astronomical Society. And I was having dinner and someone asked, "What's your favorite object?" And I always go back to uh, a set of stars called the Double Double. They're in Lyra, just to the left of Vega. There's what appears to be a star. But when you put your telescope on it, you see that, you know what? That's not a star. That's two stars that are very close together. But if you increase your magnification and you get it up high enough, you'll find that each of those two stars are also two stars. So it's a double star of two double stars. So it's called the double double. It's not a spectacular view, but it is a measurement of how good is your telescope, because you have to be able to resolve, and also how good is the sky, right? The sky, unfortunately, is made of air, and air can be hard to look through sometimes. Like tonight, what's up in the sky tonight? Clouds. That's what you're going to see when you go out tonight. But when she asked, "What's my favorite object?" that was my favorite object to look at, and it's nothing spectacular that most people would really look at, but it's just something I've always used as a "let me see what this telescope is like" object.
That's cool. Thank you. Thank you very much.
The next question is from me, and it is, why do we use right ascension when measuring the night sky?
Okay, why the right ascension? Uh, the reason it's valuable is it works for everyone everywhere. It's like longitude and latitude. Um, you know, if you were to tell somebody, "Where do you live?" you could say, "Well, I'm at the end of Maple Street near the crossroads with Oak Street," right? That would be a very local description for you. But if you wanted to tell somebody 1,000 kilometers away, "This is where I live," the much more accurate way to do it would be to give them um, your longitude and latitude. Same thing with the sky. Why we use the right ascension and declination system is you can pinpoint any place in the sky, and everybody who is looking in the sky can measure it the exact same way and find the exact same point that you're looking at.
That actually
And
makes a lot of sense.
yeah, and why we use it is, it goes back. I was trying to find out when it was first developed. They they say that who was it? Well, it's definitely in Ptolemy's Algemist from 300 AD, but it goes back even further. Longitude and latitude were firmly established in 1884, but the system was in use for thousands of years before that. Hipparchus used it when he was making maps of the Mediterranean. He would use a system like longitude latitude. And about the same time, Aristarchus was an astronomer. He did the same thing in the sky. Wasn't exactly the right ascension declination system we use now, but you know, it is to right ascension declination what uh, Hipparchus is to longitude latitude. So we've been doing it this way for a very, very long time.
Wow, that's really fascinating, actually. Next, Dev has a question.
Hello, John. My question is, how do weather and light conditions affect what we can see in the night sky, and how can one plan for the best viewing experience?
Okay. Well, um, weather is hugely important. I mean, we all know that sometimes the sky is clear and sometimes the sky is cloudy. Now, if you go to maybe you have friends at university that are studying meteorology, they'll tell you that clouds are evaporation and wind currents and this and that. Astronomers know clouds are formed by buying new astronomy equipment. If someone buys a telescope, that creates clouds in the sky. I know it. When I buy a telescope, that's what happens. When my friends buy telescopes, that's what happens. People buy telescopes at Christmas, the winter is all cloudy. I'm convinced. But light conditions. Uh, light conditions are hugely important because although the sky looks clear, although air looks to be clear, it's not, right? There are uh, little particles in the air, and any light that shines up from the ground will reflect off these particles. That's why when you're out at night, you can tell which direction is Toronto because there's a glow in the sky in the direction of Toronto. So light pollution is hugely important. If you're ever caught in a blackout at night, go outside. If all the lights around you are turned off, go outside and see what the sky really looks like. It's amazing. When we had a blackout in 2003, I stood in a driveway in Woodbridge and I could see the Milky Way clear as anything. It's just amazing. So if you ever have a blackout, instead of being scared, go look at the stars. It's a rare opportunity. But light conditions have a huge effect. They wash out the sky. Faint objects are that much harder to see. Um, how to plan for the best viewing experience is you really need to get away from the light. You got to find a dark place. Canada has several dark sky preserves. Problem is they're all published. So, I mean, I was up at Torrance Barron last summer, and the parking lot was overflowing with people. Uh, Dark sky preserves do have good dark sky, but they're um, really popular, especially if there's something like a meteor shower or something like that being advertised. Um, I'm planning on going to Killarney Provincial Park this summer. There's a night sky preserve there, or a dark sky preserve there. And of course, York University runs the Astronomer in Residence program. You get a great sky when you're there. You get a great sky at Algonquin Park. Any place where there's no light, you're going to get a better view. You can go online and look or search for light pollution map, and it will give you the Bortle ratings. Bortle is how we measure the light pollution in the sky. One is no light pollution, and it goes up to 7 or 8, I think, is just like downtown Toronto, downtown Los Angeles, New York City, that kind of thing. The lower the number you can find, the better you're going to be.
Quite insightful. Thank you.
Next, Hector has a question.
Hello, John. Thanks so much for such an interesting talk. This question may be a bit out of tangent, but I was just curious. So my question is, could you share some tips possible on transitioning from an altitude azimuth perspective to using a right ascension declination system?
Okay. So both of these systems, um, you require some kind of measurement tool, right? And this is what your telescope mount will do, right? Your telescope is made up of, basically two parts. You've got your optical tube, which um, that's what you're gathering your light with, right? You can put an optical tube on several different types of mounts, but it's the mount that decides whether you're going to be working with alt-az or um, right ascension declination. My telescope is actually an alt-az telescope because I just do visual. Right? I don't need to track the sky for hours and hours like a astrophotographer. So I have an alt-az mount, and it's simple, basic, works well. But if you want to get into astrophotography or something more serious, you need an equatorial mount, which will work off of the right ascension declination system. It will track the sky because you align it with the North Celestial Pole, and that means that as it rotates, it's not rotating flat to the Earth like my alt-az does. It rotates on an angle equal to the celestial equator. It's a much more accurate system. You can convert an alt-az telescope to a right ascension declination system with a device they call a wedge, where you basically, when I set up my telescope, I want to make sure that the base of it is level. But if I wanted to use right ascension declination, I would want to make sure that the base of my telescope is at the same angle as my latitude and also oriented directly at the North Celestial Pole. So it is possible to turn an alt-az into a equatorial, but you're probably better off deciding this is what I want to do and just buying an equatorial mount.
All right, perfect. That was really thoughtful. Thank you so much for sharing it, John.
Thank you.
And finally, we have a question from Maheen.
Thank you so much for the great talk, John. My question is, why do we still need the alt-az system for sky measurement when we just talked about the fact that right ascension and declination is globally relevant?
Okay. Why do we need it? We don't actually need alt-az. It's just a much simpler system to do and to use. If you have a tripod that you put your camera on, it uses an alt-az system, right? You can adjust, turn it left and right, and tilt it up and down. That's alt-az. It's very simple. It's easy to understand, and it's good enough in a lot of cases. Why we still need it? Well, I think we still use it because it's easy. I think it's easy to understand, and if you're starting out, it's an easier concept than the right ascension declination. But the alt-az system has its limitations, but it's still good enough for a lot of things. And it's also a much more natural, right? It's much more natural for you to look around at your horizon and use that as a basis of measurement, as opposed to trying to calculate where is that celestial equator, where is that celestial meridian. So yeah, I would say we use it because it's still useful.
Great, thank you. That was a very helpful answer.
And that concludes the questions that we had for you. So thank you so much for the presentation and the answers to all of our questions.
All
And
right,
now
thank you.
Hector will lead us out.
All right, thank you, Denelle. Well, everyone, you have been listening to the Alumni Council Observatory's monthly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening were Denelle, Maheen, Dev, Alex, Darius, and myself, Hector. All of our programs are free, but if you would like to make a donation, see our website at yorku.ca/science/observatory/. You can always connect with us on Instagram with the handle at yorku observatory and check out our website for show notes, content, updates, and contact info at yorku.ca/science/observatory/. Thanks for tuning in. Clear skies and have an excellent night.